Okay. Hello everyone. So our next topic is torque on a current carrying loop. So basically suppose a current carrying loop is rotating in magnetic field. So we have a north pole here, a south pole here. So outside a magnet, magnetic field lines are from north pole to south pole. So direction of magnetic field will be from west to east, and there is a dipole or a current carrying loop which is rotating in magnetic field. So we have to find out what will be the total force on this loop and what will be the total torque on this loop. So we'll derive the conditions for that and also the equation for that. Okay. So in this case, we have one north pole, we have one south pole, and magnetic field will be from north to south. And we have a loop in which current is I, the current is in clockwise direction. The length of loop is L and the breadth of loop is B. So if we'll apply Fleming's left hand rule, then what you'll see is on suppose this is first branch, this is second branch, this is third branch, and this is fourth branch. So if we'll see on first branch, if we'll apply Fleming's left hand rule, then the force will be in, if you'll see, the force will be in downwards direction. So on first branch the force will be in downwards direction. So magnetic field will be in downwards. Similarly, on the second part, on this second part, the current and magnetic field are parallel, so force will be equal to 0. On the third branch, if you'll see, on the third branch, the magnetic force will be in upward direction. So on third branch, the magnetic force will be in upward direction. And on fourth branch, again the current and magnetic field are anti-parallel, so force will be 0. And also on the first branch and the third branch, the current is same, the length is same, and the magnetic field is same. So formula for force is ILB sine theta. So in this case, theta is 90 degree. So the force on 1 and 3 will cancel out, and the net force, remember, the net force on a current carrying loop in uniform magnetic field will always be 0. It doesn't matter whether the loop is circular, square, triangular, hexagonal, trapezoidal, or even the shape of amoeba or bacteria. It doesn't matter. If the magnetic field is uniform in nature, the net force on the loop will be equal to 0. In this case, I have proved that for a simple rectangular figure, but please remember this thing, net force on any current carrying loop, it be of any shape, but the magnetic field should be uniform, will be equal to 0. Remember, net force will be 0, not the torque. So now we'll find out what will be the value of torque. So in this case, if you'll see, we have one north pole, we have south pole, and magnetic field is from north pole to south pole. Now current here is in anti-clockwise direction. So I, and I. Length is L, breadth is B. If you'll see on this branch, on branch number 1 and branch number 2, the force will be equal and opposite. So if you'll see on the below branch, the magnetic field will be downwards. If you apply Fleming's left hand rule, the magnetic field will be downwards. Okay, and on the upper branch, the magnetic field will be upwards. So both these forces will cancel out, and also they will not provide any torque because the force is passing through the axis. But if you will see this branch, suppose branch number second, okay, third, and branch number fourth, if you'll see both these branches, then current and magnetic field are perpendicular. So on this branch, current is in downward in this direction, magnetic field is in that direction. So if you'll see, the force on this branch will be ILB and it will be in upward direction. The force will be ILB and it will be in upward direction. And on the fourth branch, the force will be ILB and it will be in downward direction, because angle is 90 degree and formula for force is ILB sine theta. So now what will we do is, if you'll see, this is a couple. So what is a couple? Couple is a system when there are two equal and opposite forces applied at a distance from each other. So if we'll see, this will rotate. So how will we find the torque? So torque is basically force into perpendicular distance. Force we already have ILB. Now how will we find the perpendicular distance? Suppose this is magnetic moment M. So M is perpendicular to area. This is magnetic field B. and the angle between M and B is theta. So if this is theta, then this will be 90 minus theta. So this will also be 90 minus theta, and this is 90, so this is theta. So the side which is opposite to theta will be, this will be B sine theta. So torque will be force into perpendicular distance. So perpendicular distance is B sine theta, because one force is in this direction, another force is in this direction. And what will be the perpendicular distance? The perpendicular distance will be this. So this comes out to be B sine theta. So ILB into B sine theta, L into B is area. So IAB sine theta, and I into A, current into area, is magnetic moment. Please remember, I into A is M. So torque comes out to be MB sine theta, where M is magnetic moment, B is magnetic field, theta is the angle between magnetic moment vector and magnetic field vector. Okay. So tau is basically mb sine theta. M is a vector quantity, B is a vector quantity. So we can also write out tau to be equal to m cross B, where m is magnetic moment vector. We have already calculated, we have already learned how to calculate magnetic moment. So magnetic moment is NIA, number of turns into current into area. So for our derivation, we took number of turns to be equal to 1. But if n is given, you can put the value of n. So m is basically NIA, NIA. And what is theta? Theta is angle between normal to area and magnetic field. And remember, if current is clockwise, then magnetic moment will be inwards, and if current is anti-clockwise, then magnetic moment will be outwards. Okay, so you have to remember this formula for torque, that torque is equal to mb sine theta. And also remember one thing, if magnetic field is uniform, net force will be equal to 0, net torque will not be equal to 0. It will depend on theta also, because if theta is 0 or pi, then torque will be 0. But if the field is non-uniform, if the field is not uniform, then net force will also be not equal to 0, and net torque will also be not equal to 0. Torque depends on theta, so there can be two cases at which the torque will be equal to 0, but in general condition, torque will not be equal to 0. Okay, so please write down this derivation. This is a very important derivation, and if you have any doubt, you can discuss it with me.